Okay, video's rolling, so I'm recording that just because I really ran out of time period 1 this morning. I'm going to post something for them to watch if you ever need to go back and watch this again. Let's work on the Bellwork question, page number 394, number 78. Okay. Cesium fluoride reacting with xenon. What do we know about xenon? Anybody? Connor? Noble gas. The noble gases usually don't react with anybody, right? Xenon has been found in the last 15 years that scientists zap it with enough electricity, get it with enough energy in those electrons, they can make it react. It's one of the exceptions to the rule. It does what we call an expanded octet. I didn't teach you how to do this, so don't worry about it, but if you tried to draw a picture of this, I didn't show you how. It's a different shape. It's not your tetrahedron, it's not your bent, it's not your trigonal pyramid, it's something different. I think this one is a octagonal thingy, octagonal pyramid. Okay, so, but it's weird. So we got xenon and 3 fluorines reacting together. Xenon hexafluoride, definitely covalent, 2 nonmetals. And when we put them together in a synthesis reaction, we get cesium, xenon, heptafluoride. Crazy, right? Okay, first step is always balance the equation. Okay, balance it for me. 1, 1, 1. What? Too easy, okay? So this one's already balanced. And what we need to do is figure out what are we given, how many moles can be produced. If I have 12.5 of this, and 10 moles of this, how many moles, question mark, doesn't say grams, so it says how many moles. That makes it nice and easy. That makes it nice and short, because it's going to be once we figure out which one's the limiting reactant, now it's a one-step process, right? On our flow chart, it would be step 2 to step 3. So the first thing we need to do is determine which one's going to run out. Now remember the nuts and bolts activity we did last Thursday, right? Nuts and bolts was to get you in the mind of thinking something's going to run out, something's going to be left over. And so these numbers are not necessarily the exact quantities or they're going to react with each other. We need to change them into moles and then figure out which one we're going to have extra of, which one are we going to run out of. And I showed you this last week. Number 1, they're already in moles. Ta-da! If they were in grams, our first step is always change them into moles with the molar mass. In this case, we're just going to divide the 2. I'll take 12.5 moles of CSF and divide by 10.0 moles of XEF6. Now this is called the given. This is what I have. This is what I'm supplied. This is what I start with. However you want to word it, this is physically what I'm putting into something to react, into a beaker, into a crucible, into a chamber to react. The question that we want to compare that to is what do I need? What's the ideal ratio? What's the theoretical ratio? What's the optimal ratio at which these two things react with each other? And the balanced chemical equation always tells us that. Coefficient of 1 to 1 to 1. Okay? So, in this case, I'm given a 1-to-1 reaction ratio on the reaction itself. So I'm going to write these in the exact same order, but it's going to be 1 mole of CSF requires 1 mole of XEF6. Okay. Now, before I can compare these, they have to have the same denominator. You can't compare 2 fractions unless they have the same denominator. If you say which one's bigger, 5/6 or 11/12, or I mean, you can't compare them until you get to be a common denominator. So the easiest way to do that is divide these two numbers. 12.5 divided by 10, 1.25, right? So this is a 1.25 to 1 ratio. I could write moles, but I'm just going to shorten it a little bit. This is what I'm given, and this is still 1 to 1. 1 divided by 1 still is going to be 1 all day long. Okay, so here's the thinking part. Here's where you have to look at these two numbers and figure it out. Okay? Comparing this to this. This is what I have. This is what I need. Now, you can literally write this down and get in the habit of asking yourself, do I have enough CSF? Do I have enough or more do I have more CSF than I need? And really just ask yourself that question. I'm comparing this number to this number. Is this more than enough or is this not enough? And really, that you just have to ask yourself that question. Okay, and it will tell you. If this number is more than enough, then I've found the excess. If this number in the numerator is not enough, then I've found the limiting reactant. And depending on which way you do this, sometimes you'll find the limiting reactant and the other one is the excess, and sometimes you'll find the excess and the other one is the limiting reactant. In this case, this is more than enough, right? My 1.25 is bigger than 1, so I got extra of the CSF and not enough. The other one has to be the limiting reactant. So we'll go all the way back to the top and label that chemical reaction. Okay, excess right here. Don't need that number. Limiting reactant. This is the one that's going to control how much of that is produced. Okay, it's like on your nuts and bolts. When you ran out of bolts, you couldn't make any more. Or when you ran out of nuts, you couldn't make any more. You might have had some leftover pieces, but you couldn't make any more of the compound once you ran out of one thing. Same thing. This is going to be the one that's going to run out and stop the reactions. The reaction can't continue unless I have both reactants present. So when this is all gone, the reaction stops and I can calculate how much of this we produce. Good? Now that I know this is my limiting reactant, now I can do the stoichiometry problem. And we're just going to go back to what we did last week. I'm going to take 10 moles of this and figure out how much of this is produced. And using your flow chart, should be pretty simple. 10.0 moles XEF6. Mole ratio. 1 mole CSXEF7 is produced for every 1 mole of XEF6 that reacts. And 10 times 1, everybody? 10. Yeah, so the answer is 10.0 moles CSXEF7. Box around it. One more time. Okay.
Some homework, or on both problems in homework, it said the excess reactant. How do you find that? It's like after it said after the whole equation's done, what's the amount of excess reactant?
We'll do one like that today.
Okay.
Okay. Questions other than that? Okay. That's the bell work. Put it away. Let's take a look at a couple of things. This is for you later. I want to talk about the video for a few minutes, get some feedback, and open a discussion up just for about 5 minutes here. I do not randomly choose things to show you when I'm gone. I choose them for a very good reason. And this one was kind of to make you think about something. In general feedback about what you saw Friday and over the weekend in this video, the great global warming swindle. Sound reasonable? Have you ever heard anything like that before? Has anybody ever experienced a debate about those types of things? Okay.
Well, everybody like tries to debate about it, but like nobody knew like the actual science behind it. Like, it shows you everything of like what's actually happening.
Yeah, it's a big deal, and of course, in today's world, it's about all you hear about sometimes. Has anybody ever looked at the issue in detail. Okay, you guys are almost voting age, 18, right? So you're within a year of that, most of you. And when with age comes responsibility. With responsibility is big when it comes to making up your mind about what you believe. Okay, and that's important in all areas of life, whether that's science, politics, faith, religion, salvation, all those things. You have to make up your own mind. You can't go through your whole life saying, you know, all my friends believe this, so I guess I will too. Okay? Because that many times is not the best way to make up your mind about stuff, right? You want to know what you believe and why you believe it. Okay? In my personal experience, when I was presented with the gospel at the age of 29, it totally blew me out of the water. Somebody challenged my beliefs, and I had to evaluate, why did I believe what I believed? Why did I not believe in God? Why did I mean, I was basically an atheist. I didn't believe the Bible. I just thought it was a book. I believed Jesus was maybe a guy that lived 2,000 years ago, and that was it. But, you know, I didn't believe anything, because I had believed a lot of what the world teaches in today's world. And you guys are kind of sheltered here in Alabama, because this is the heart of the Bible Belt. But in most parts of this country, if you profess to be a Christian, and like publicly, I mean, people look down on you. They literally consider you an imbecile for believing in God. And that's big all around the world, but also, especially here in the United States, it's more and more what we call a secular society. So if you know why you believe what you believe, then you can be courageous. Then you can be strong. Then you can know that you don't have to shirk from somebody that has a different opinion than you. You can have an educated conversation. You can debate with them. You can talk about them in a civilized way and express your point of view. And whether they accept it or not is up to them, right? It's completely a free speech and free thought society so far. So I wanted to challenge you on Friday with this video and show you the other side of the story and make you think about what you believe, maybe, because this is a huge issue that's affecting nations, it's affecting politics, it's affecting budgets for countries, it's affecting everything. So I just want to point out a couple things, and again, you're welcome to your own opinion, but there is a silenced majority. And you may have heard maybe somewhere on the news that 97% of scientists believe in anthropogenic global warming. That is a fallacy. That fact, that 97% number, goes back 20 years to a study that was done in 2003 where it comes down to about 67 scientists believe this was true. And that was 97% of 82 or something like that, okay? So it's a really small number. And every year that goes by, and if anybody's interested, you can see me after class. I have hundreds of websites and different things, different resources and books and stuff like that you can access that say, this is not what the facts show us. Now, every side of the story has two sides, whether it's Christianity and Buddhism, or Christianity and Mormonism, or whether it's Republican and Democrat, or whether it's pro-life and pro-choice, or whether it's global warming caused by CO2 emissions, or global warming caused by something else. Okay? All of these issues have two sides, and you as a person, as an adult, as a person who belongs to society, you need to know, what do you believe? Because it's going to affect how you live your life, what you teach your kids, and how you vote. And why do you believe that? Right? So these are big issues. And I wanted to bring up this word right here, bias. Bias is something all of us have. If you're an Alabama fan, you're biased towards Alabama. You can't say anything bad about Alabama in your presence because you're going to stand up for them. And that's a bias. That's okay, as long as I know that, right? And if you're an LSU fan, then I need to know that too, okay? So bias comes growing up in a Christian home. If you did, you're biased towards Christianity. That's probably all you understand and know. You don't understand what a Buddhist believes, or maybe you don't quite understand what's different about Mormonism, and the fact that Joseph Smith looked through a magical hat at some golden plates with hieroglyphics on them he found buried in New York State in 1831, and therefore wrote the Book of Mormon from those hieroglyphic plates that nobody's ever seen, nobody's ever found, and he purports to do. I mean, it's just, okay, why can I believe that and not the Bible? Okay, so there's a bias in every point of view, and if you understand the bias that you have and understand the bias that the other person has, then you can have a good conversation. I want you to notice that in the video they brought up a couple things. Bias on both sides of the debate always goes back to money and jobs. And there was an illustration just 2 years ago in the news here in the Southeast. There was a professor at at Georgia Tech. Georgia Tech is one of the top 10 engineering schools in this country. And this gal was very, very well known. She taught climate science, basically, all the courses that have to do with climatology and stuff. And she had been on the bandwagon for years, and finally she came out and published some papers that said, no, NASA's fudging the numbers, and this is not true, and this is for political reasons, and she got canned, literally. She was a big, big name in this industry of climatology. And this was literally 2 years ago. Pretty sure it was about 2 years ago. I could look her name up right now. But so that kind of thing happens. If your job depends on towing the line on a certain issue, and you don't agree, you need to know you might lose your job, and that will keep a lot of people saying the same thing. Alternately, money drives everything. You might have heard one of the guys in the video say, you know, people blame us for accepting money from oil companies. He says, I wish, right? You can't just make a blanket assumption that if you're on the other side of the debate, you're accepting money from somebody who wants you to say that. And he said, no, that's not the case. So you have to ask the hard questions, you have to follow up on the facts, you have to double check everybody's facts, and then you have to come to your own conclusion. So the money is always a big issue in any debatable issue. Whether it's the fact that Planned Parenthood makes millions of dollars, hundreds of millions of dollars a year on what they do, or whether it's Democratic or political or Republican fundraising, or whether it's science and getting grants. You gotta realize professors at universities spend most of their time not teaching. They spend most of the time doing research. And the research portion of their job is not paid for by the university, it's paid for by grants. And grants are money that comes from the government to do the research. And so professors, somebody asked me recently, why don't you quit teaching in college? I said, I don't want to spend my life raising money, okay? And begging corporations and governments for money. Okay. So I wouldn't want to do that, but people do that, and that's how they're funded. And so when your livelihood depends on getting grants, many times they'll tell you, well, we'll give you the grant if your research is about this subject, because we need more information on that. And that's where this whole global CO2 thing has gone round circle. And all the research that's being done today is to support the fact that people believe CO2 is warming the planet. Hopefully there's enough facts, and I believe there was in that video, but again, there's a lot of more resources available if you want to look into it. It's easy enough to Google, and I just want you to have an open mind about it, okay? People say the polar bears are dying. No, they're actually thriving right now. They really are. The sea levels are rising, we're going to drown. No, actually, 1 millimeter a year for the last 85 years, and it's still going 1 millimeter a year. No, it's not changing. What else is going to happen? We're all going to die someday, but that's not because of the atmosphere. There's going to be a massive drought. Actually not. More of the earth is green today than it was 30 or 40 years ago, because CO2 helps what? Plants grow. Trees are blossoming everywhere, plants are growing everywhere, farms are capable of growing fruits and vegetables further north than they have ever been. So there's all kinds of contrary information. And if you believe that the hurricane season is getting worse, statistics show it hasn't. Are tornadoes getting worse? No. Statistics, the numbers show they haven't. Is flooding getting worse? No, it's not. Okay, and again, you have to look at the data. Every time you see a sensational news piece, it's like, oh, this is because of global warming. No, it's not. Okay, most of the time. Is the world warming up? I will not deny that. But again, the Earth has gone through many times of warming and cooling throughout the years, and we're coming out of a mini ice age. We are at the tail end of an ice age right now, so we are going through a warming phase. That will happen. What caused the ice ages? Anybody know? Variations in the Earth's orbit and the tilt of the axis over tens of thousands of years causes these changes in variation of the temperature of the Earth. Anyways, if you have questions, glad to talk about it. It's a cool subject. It's kind of one of my pet peeves about science. Anybody not here Friday? Okay, you don't have to make this up, but it's worth 20 points to you if you fill it out, turn it in. You can grab one for class. Good. Take out your notebooks. Let's talk about stoichiometry and limiting reactants. I want to do 2 problems. Before I get back to 2. And I'm not sure if I've done this one in this class before, but for some reason it sounded familiar. It seems like period 6 would have been the one I did it with. But number 76, the photographic plate, or 72, photographic plate. Does this sound familiar? Let's see if it does. I don't remember if we did it right. First thing, write the reaction out. And make sure it's balanced. And in this case, on number 72, on page 394, it gives us a 2 coefficient here, so there's 4 sodiums, 3 plus 1 sodiums, 1 silver, 1 bromine, 1 bromine. And this thing here, guys, is called thiosulfate, THIO. It is a polyatomic ion. So that's why you see S2O3 over here and S2O3 over here. Okay? Not one I had to memorize, but it's pretty common. You'll see it frequently. The question here says, determine the mass of this stuff. Now, this, I don't know how to pronounce that, so I'm going to call this stuff. Okay? And so we're going to call and say how many grams of stuff are produced if we start with 0.275 grams of this. Okay, so quick review from last week. We're going to do a stoichiometry problem here, and this is not a limiting reactant problem. Okay? 0.275, starting point, grams over 1 of AGBR. We're going grams to grams, so 3 conversion factors. You should be in the habit of writing those out. Starting to fill them in. First one's going to be grams per mole every time. You should be able to kind of fill this all in without even any numbers. We can come back and fill the numbers in a minute. Mole ratio. How many moles of that to this? 1 to 1. 1 mole of stuff per 1 mole AGBR. And the third one's also a molar ratio, but this one's going to have the grams in the numerator. We've done a bunch of these problems. You see the pattern per 1 mole of stuff, okay? Grams of stuff per mole of stuff. So this is what my conversion, my stoichiometry problem is going to look like. We just need to calculate this. Bromine is about 80. Silver is about 108. So 108 plus 80, everybody? 188, good. So then my first molar mass, this one goes down here. And on the stuff over here, you got to add all that up, and I'm going to trust somebody who did it first period this morning. They said 401. Okay, so I'll still use that number whether it's right or wrong. I think it was Isaac McCory that calculated it, and we'll figure it out. We'll blame him if it's wrong. Okay, so again, once we get our numbers in there, we calculate our molar mass for what I started with, molar mass for what I'm ending with. In the middle is my mole ratio. We check. Do my units cancel out? Yes. Do my units cancel out? Yes. I did one of these last period, and I'm going, man, I caught a mistake right in the middle because grams didn't cancel out with moles. Okay? Moles of stuff, moles of stuff. We're good. So 401 times 0.275, and then you divide by 188. Caden's crunching the numbers right now. Looks like we got. My work is sloped. No?
0.587.
Yes.
And then 400.
Grams of stuff. Okay? 587 grams of stuff. So quick review problem here. Stoichiometry. Now, limiting reactant. Let's do this. I'm going to pass out tonight's handout, okay? We've got a few problems to work on this tonight, but I'm going to do one from this worksheet, to save you some time on tomorrow's homework. Yay! Because tomorrow night we all want you to go to basketball game. Yay! So I'll do one of your 4 problems from tomorrow night's homework. And then you'll be able to double check it. Okay. Now, turn to the side that has 7 problems on it, and we're going to do number 4, so you can follow along. This problem starts very inconspicuously. How many grams of aluminum sulfide are formed when 5 grams of aluminum is heated and 10 grams of sulfur? What's missing? The reaction, okay. So I'm expecting you to know how to write this reaction. Yay. Okay, somebody tell me what the reaction is. It's really not that hard.
Al plus S yields Al.
Yeah, it's a synthesis reaction, so we're going to go with Al. Thank you, Mr. Malone. Al plus S produces Al2S3. Ta-da! Now, we do need to balance it. Amelia, how would I balance this?
A 2 in front of the AL and a 3 in front of the S.
So hard. Okay, so far, so good. We got a reaction. We got a balanced chemical reaction. Next, I'm going to label this. What am I starting with and what am I looking for? So 5 grams of this. Put it underneath it so we know what that is. 10 grams of this. And then we're looking for how much of this? Question mark. So I have 2 things given, limiting reactant problem. Good? So first step, always, Kenzie?
Divide those two, the reactant numbers.
Mm-mm. Not yet. The last problem we did that first because we already had units that were different than this. First step though, change it to moles, okay? Then we can do that. So always start by changing it to moles if it's not. The last problem we did was already in moles, so that was our first step. This one's not. So molar mass of sulfur, molar mass of aluminum. Let's do this quickly here. We got aluminum 27 and sulfur is 32. Now we have moles, okay? And this one here, 5 divided by 27. What do you got?
0.185.
Okay, 185. And this one, 3125 actually. This is actually a fraction 10/30 seconds. 10/30 seconds reduces to 5/16. And so if you know your fractions, that's 5/16. Okay, a little bit more than 4/16, which would be 0.25. 0.25 plus 0.125. I think it is 0.325, right? 325 or 3125?
3125.
Okay. Anyways, so here's our 2 moles. Now we're going to do what Kenzie said. Now we're going to divide these. We're going to write down what do I have or what am I given. Either I switch back and forth between those 2 words. And what do I need? Okay. What do I have? What am I given? Okay. So it's going to be on. I always like the number to be more than 1. So I always pick the big number over the small number. You don't have to do it that way. I showed you last week. You get the same answer both ways. But I'm going to put 13125 of sulfur. make sure you label it, because you need to make sure you get the second one the same, over 0.185 moles of aluminum. I'm going to compare that to the reaction. The reaction tells me the coefficients of moles of sulfur to moles of aluminum should be 3 to 2. Sulfur over aluminum. Okay? You with me? Raise your hand if I'm going too fast. Okay. Now, I cannot compare these two numbers unless they have the same denominator. So we literally get the calculator out and divide these two numbers and divide these two numbers. Okay? First one here, 0.3125 divided by 0.185. 1.7 roughly, 1.689. We'll call it 1.7 over 1. This one is going to be 1.5 over 1. Do that one in your head, I hope. Okay? So here's my two ratios. This is sulfur to aluminum. This is sulfur to aluminum. They both have to be in the same order. And here's where I ask myself the question. And I'm going to ask you this question. Do I have more than enough or not enough sulfur? Kayla?
More than enough.
More than enough. You got 1.7 bigger than 1.5, so this is my excess. And the other one, aluminum, is going to be the limiting. So excess sulfur, ignore. Limiting, use this number here to do my stoichiometry. Okay, so now we're going to go back and we can do the stoichiometry problem using 5 grams of aluminum. How much is this going to be produced? Let me just shrink this down so we can still see. It worked this morning. So, 5.00 grams of aluminum, 3 steps equals that. Okay, so the first step is going to be the same as what we did up here. We're going to divide by 27 grams of aluminum, 1 mole of aluminum. The mole ratio is going to be moles of Al2S3. I think that's a 1, right, for the coefficient. And the coefficient of aluminum, 1 mole, 2 moles of Al. Okay, third step, mole ratio of Al2S3. That's 3 times 32 for sulfur, 96. 2 times aluminum, that's 27 times 2 is 54. So 96 and 54, something like that. 150. Yeah, so it should be 151 grams of Al2S3 over 1 mole of Al2S3. Step number 5. See if my units cancel out. Grams, grams. Good. Moles of aluminum. Yes. Moles Al2S3, moles Al2. Yes, I have everything in the right spot. Calculator. 5 times 151 divided by 27 divided by 2, or I can just divide by 54. And we will get the answer. 5 times 151 divided by 54. 13.98. But I need 3 sig figs. 14.0 grams. Okay, limiting reactant problem. Questions? Okay, my goal is to do more of these. Okay, I'll put a little twist in right now. I'm going to solve one more. I'm going to take this problem and we're going to adapt it to answer Caden's question. We'll do more of these tomorrow. On Wednesday, I'll show you how to do a percent yield problem. We'll practice those Wednesday and Thursday, and Friday's our test, okay? Okay. Now, here's what Caden was referring to. Sometimes these questions say, if this is the case, how much of this is left over, right? Since this is excess, I started with 10 grams, all of it's not going to react. I'm going to have some left over, like your nuts and bolts. I got 3 bolts left over. I got 12 nuts left over, whatever the case may be. Okay, so how do I know how much of this is gonna be left over once this reaction stops going? It's gonna stop going when this runs out. I'll have some left over of this. How do we figure that out? We got one more step. Okay, I'm going to show you how to do that right now using this problem. Extend the page here. What I have to do, since I already have this right here, I'm going to do exactly the same thing, but instead of figuring out how much Al2S3 is produced, I need to know how much exactly of the sulfur is going to get used up. And then I'm going to subtract that from the 10 at the end, right? So, I just do one more stoichie. So here, how much excess? Stoichie, that's fun. How much excess? So, we're going to start with 5 grams of aluminum. Change it into moles. Take the mole ratio for sulfur to aluminum this time. Now I want to know how much sulfur is reacting, not how much Al2S3 is produced. So that is a 3 to 2 ratio. 3 moles of sulfur per 2 moles of aluminum from the reaction, right? 3 to 2 were my two coefficients for sulfur and aluminum. And then how many grams of sulfur? 32 in 1 mole. So, same thing we just did, except now I'm doing sulfur instead of Al2S3. 5 times 3 times 32 divided by 54. 8.8. Get a different answer this morning. Okay, the sulfur reacted. That's not my answer. The question is, how much is left over? Well, how much did I start with? 10. So what's the answer? 10 minus 8.8. So the excess is going to be 10.0 minus 8.8 equals 1.2 grams of sulfur left over. 2 separate words on leftover, by the way. Okay, so you will see a lot of questions that ask you that type of problem, including tonight's homework problems, which is why I just did this for you, period 1. Okay, so how much is left over? You do one more stoichiometry with the thing that you're trying to figure out, subtract it from what you started with, and that will give you the excess amount. Good, let me shut that off.
Hi, period 1.